Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome to session 2. By the reduced strength of this place, I'm assuming that I have hopefully haven't driven people. I am just assuming that people have other things to do. Yeah. So that's a conjecture. So even if you didn't show up for session 1, it's not really a big deal. In the first 5 minutes, I'm going to quickly review what I said in 1 that is sufficient, that is necessary to understand this stuff. Yeah. Okay.
Some of us are slow, unfortunately.
Pardon?
Some of us are slow, so it takes us a while to get.
Yeah, actually, one of the major feedbacks that I got from the last time was to go much slower than what I did last time. So I'm going to try to do that. Yeah. So actually, pardon? Just stop. Yeah, okay. Okay. So the last time I talked about temporal logic model checking, and the main question that I'm trying to address is whether a model M satisfies a temporal property phi. And the way I'm structuring this course is that in the first few minutes of last time, I talked about what temporal logics are. I gave some examples of those. We went in detail through one temporal logic, and I just gave a listing of the complexities of model checking for various temporal logics. The most important part of the course really is how to handle really large M, which is a state explosion that arises in M, which is what we started doing last time, and we're going to do more of that today. And next time we're going to talk about M that arises from software. So what is M? So what is M? So is that a keyboard? Yeah, there is. So what we did last time was we first described what M is and what phi is. So this is what I'm doing now is just recap of what M is. To me, M is just a state machine, but which is labeled, which means that each state has a bunch of atomic propositions, and these atomic propositions are what really the propositions that the logics can refer to. So the formula phi can refer to those propositions in M. And for convenience, I define something called a color, which is a valuation to all these atomic propositions. So each of these atomic propositions is true or false of every state. And the sum total of those valuations gives rise to a color. So if there is k propositions, there's going to be 2 to the k colors. And each state has a particular color. And then we talked about different logics and the complexities of checking, model checking those logics. And the simplest logic is invariant, which is the syntax of invariants are the same as propositional logic, where you have just formulas, disjunctions, conjunctions, and negations of those. And the model checking problem for invariance is a very simple one. A model satisfies an invariant if all the reachable states of the model, starting from the initial states, satisfy the invariant. So there was some concern that invariants are not necessarily powerful because you can't say interesting things with them. That is true, but with one caveat, which is the fact that if you're willing to change your model, then you can pretty much state any safety property as an invariant. There's actually a theorem. You can actually prove it. So for instance, suppose you want to prove that whenever there's an event P, after P happens and before Q happens, R should necessarily happen. Suppose you want to state that. What you could do is that you could have like a bulb in your program that goes on whenever P happens, and then the bulb goes off if R happens. And now you could say the invariant, it's never the case that Q happens and the bulb is on. Right? Now you could say there's an invariant. So if you're willing to add state to your system, you could pretty much state any safety property as an invariant. And then we looked at other logics. Some logics have more complicated decision procedures than others. Some of them are so complicated that people haven't even figured out the exact complexity of checking these. And you could also state properties as state machines. And then you could have a decision procedure to check whether a model satisfies the property. In that case, the checking is called refinement checking. Then what we did was we talked about the state explosion problem and techniques that help deal with the state explosion problem. And the last time we dealt with two techniques, symbolic techniques. And when I was dealing with all of these things, I was just assuming that I'm going to check invariance. Though that makes it simple for me to explain these things. Though these techniques can be used to check any of those logics. And there's papers you could find for each one of them. Symbolic techniques handle state explosion by not representing the state explicitly. That you represent sets of states as functions and have compact ways of representing the functions. Of course, the representations are not always compact, but for certain domains, they work out very well. Partial order reductions, where you don't explore the entire state space, you explore only a portion of the state space. Using you explore if two sequences are sort of equivalent from a partial order sense, you explore only one of them, and that in asynchronous protocols, it gives you a lot of reduction. So today we're going to talk about symmetries, which is the other sort of automatic technique, and then we go to methodological techniques, which require more action from a user. So the user has to actively do more things for these things to work, but the potential of these is usually much higher than these. So that's where we are right now. So we're going to talk about symmetry reductions. So now we're going to jump in. What are symmetry reductions? So the basic idea of symmetry reduction is that if a state space is symmetric, we need to explore only a symmetric quotient of the state space. There's no need to explore the entire state space. I have to first define what I mean by a quotient. And the notion of a quotient is useful in abstractions in general as well. So, but let me define quotients first, and then I'll come back to symmetries. So recall what our model is. Our model is a set of states, a set of initial states, a set of arcs, and then a set of atomic propositions, and then there's a labeling function that maps each state to a color, right? But sometimes I can just fix the colors and just say that my colors are just constant for any system that I take. So what is a quotient? A quotient is just an equivalence relation on the state space. So I'm going to assume that the equivalence relation satisfies one nice property for me, which is the fact that if I say this is my state space, then what my quotient is my quotient is some partition of this. So the one assumption I'm going to make is that if two states are on the same partition, then they are the same colors. From an external observation point of view, they are the same. And if one of them is initial, the other one is initial as well. So either all the states in a partition are all initial, or all of them are not initial. So I'm going to assume that my equivalence relation has that property. If my equivalence relation has that property, then actually I can define what the quotient of M with respect to the equivalence relation is. The quotient has one state for each partition, and you draw an arc from one quotient state to another if there is an arc from some state in one partition to the other state to some state in another partition. So if there's an arc here, then you draw a red arc. So that's how we define the quotient state space, right? So R prime. Yeah. So but this means if for any S prime, the equivalence class of S prime will be the same as the equivalence class of S, right?
But S may be wrongly chosen.
That's right. So but then S and T is wrongly chosen means that there could be R S prime T prime, right? But S prime, the equivalence class of S prime, and this are the same thing, right? You know. You could have self arcs. For instance, if there is an arc from here to here, right? Then it means that this will hold as well, right? Okay. So the only thing I said is that if I give you an equivalence relation that sort of respects these things, then I can construct a quotient.
But the funny thing is that there could be a path
Yeah.
quotient machine,
Which is not. That's you are jumping 3 slides ahead. That's right. That's the correct observation.
It's not manifested
In the original one. So
you don't have a transitivity rule.
yeah.
Transitivity doesn't.
So what happens is that, so why am I doing this? The reason why I'm doing this is that, suppose I want to check whether some invariant phi holds, right? So actually, for most of this talk, right, when I say satisfy phi, right, just assume that phi is an invariant. So what I really mean is that maybe this is the set of states that satisfy not phi, right? The question is, and maybe these are the initial states. The question is, from the initial states, can I really reach not phi? That's the question that I'm asking, right? And what Tom was saying was that what I want to do is, instead of checking whether M satisfies phi, I want to check whether the abstraction satisfies phi, right? But these two questions are not equivalent. But it is correct in one direction. It is not correct in another. Right? If there is a bug, this technique will find it, right? Because, for instance, if there is a way to get here and then to here, then it definitely means that in the abstract state space I'll be able to do the same thing. But the other way is not true, right? Suppose these two exist, then the structure could really be this in the concrete state space. So if there's a path in the abstract state space, it doesn't necessarily mean that I could have a corresponding path in the concrete state space. Yeah.
So there's some analogy here with respect to merging and data flow, right? Because what we've actually done is we use these equivalence classes as sort of merge points.
Yes.
Right? So in the original state space, you were looking at each path separately.
Yes.
And now because you merge, when you come inside an equivalence path, you lose that
That's right.
content.
That's right. Yeah. So you have lost information by doing this abstraction. I see the analogy there as well. So so you could have more precise abstractions if the equivalence satisfies one other property called stability. So what are stable equivalences? Stable equivalences have the additional property that I should use the same color. Has the additional property that, can everyone see this? This is fine, right? Okay. Stable equivalences have the additional property that if there is an arc from some s to some t, then it also implies that from every state here there's an arc to some state here. And also if they say if there's an arc from here to here, then it means that from every state here there's an arc to some state here. So that is a stable equivalence. Suppose the equivalence is stable, then you don't really lose information. So in this case, right, suppose there's a path from here to here and here to here, then it means that from any initial state I can go here. And now because there's a path from here to here, it means that there must exist an arc from here to somewhere in here. Right? So in some sense I get both soundness and completeness. So why did I talk about stable equivalences? There are several natural stable equivalences that can show up in model checking, and symmetry is one of them. So symmetry, understanding stable equivalences is a very easy way to understand how symmetry reductions work. Mm-hmm.
So this, I don't remember really understand what the restriction is.
It's too strong. You said that it's stable if there's an arc from the abstracted space from one equivalence class to another, then for every point in the source equivalence class, there is an arc to some point in the target.
It seems too strong, yeah.
And that's, yes, it does seem too strong.
So I'll give you one illustration of where it can be useful. Okay? Yeah, it seems too strong. And there are not that many stable equivalences that you can just naturally just come up with. But there are some, and symmetry is one of them.
Can I try to make an analogy here?
Sure, yeah.
Suppose in a program you have two branches, okay, one after the other.
Mm-hmm.
So that can give rise to 4 different paths.
That's right. Mm-hmm.
Okay, so here what you're saying is that if you think of those two branches in the equivalence thing, okay, then you've got all 4 combinations actually exist. All 4 paths actually exist, and so you can merge those two things together and lose no information.
Yeah. So you might not be able to do it all the time. Yeah. Do you have? Okay. So what I'm going to do is I'm going to talk about symmetries and then convince you that symmetries give rise to stable equivalences as well. To define symmetries, I'm going to talk about automorphisms. So these automorphisms are functions, permutation functions on the state graph, right? So a function, a permutation function on the state graph is an automorphism if I have S and T, then if I have f of S and f of T, right? There's an arc between S and T if and only if there's an arc between f of S and f of T. That's the definition of automorphisms, right? So can you identify automorphisms in this one? So the one thing I have to apologize is that in the next 3 or 4 slides, I unfortunately did not take coloring into account, right? So do they have to preserve colors? So for the purposes of this discussion, let me just assume that I have an underlying graph, and I'm not going to talk about colors. So just ignore the fact that there's an yellow there. So the automorphisms in this graph are the one that map the top state to the bottom one, right? And the one that's F, and the bottom to the top, and the one that map to the left to the right and the right to the left is G. The composition of those two is also an automorphism. The identity function is also an automorphism. In fact, those are the only automorphisms in this graph. Right? And in fact, in any graph, right, the set of automorphisms form a group with respect to composition. Right? Okay. So now, using these automorphisms, I'm going to define an equivalence on the state space. Equivalence on the states of the graph. Right? Let me just say that 2 states are equivalent if there's an automorphism that maps one state to another, right? So if you go back to this, what I'm going to do is I'm going to take the state space and then I'm going to draw equivalence classes in such a way that if there's 2 states in an equivalence class, then it's necessarily the case that I can go from one to another via some automorphism, right? Then the claim is that the equivalence that I create this way is indeed stable. Why is that? That's because, say I have S, and there's an arc from S to somewhere here, right? Say to T. Okay? Let me take any other state here. That means that there is some F such that S maps to this one, right? With the same F, there must exist some other state Ft, right? And that has to be in the same equivalence class, right? By definition. And because it's an automorphism, there must be another arc here as well, right? So these equivalence classes are usually called orbits, right? And the claim is that they are stable. So the orbits in this case are. You had something else?
No, finish that thing out.
Yeah. So the equivalence. So this and this together and this and this together. And what you could do is that if you could find the orbits, then you could sort of collapse each state to its representative in the orbit, and you get something that's a very strong reduction in the sense that you could actually check invariance on this, and you wouldn't be losing any information at all. Right? Yeah.
So, is it the idea then that when you have equivalence classes like that, like you just showed, like the automorphism rule, all those different things in one equivalence class are really indistinguishable from each other in terms of what transitions can arise from.
Yes, and that actually arises a lot in protocols and hardware. For instance, right, I'll give you a couple of examples. Right, if you're talking about exploring the state space of a microprocessor, for instance, the registers are really symmetric all the time. Right? If you have like 8 registers, 8 general purpose registers, right? Not all of them, right? Not all of them. So the general purpose registers are all usually symmetric, right? If you're talking about a protocol which is a ring topology, right? There's a lot of symmetry in there. So see in hardware and protocols, there are certain pieces of the hardware that you can just take that are by intention symmetric, and those are the only sort of things that you're going to be able to use with these. Yeah.
The effect is yours, but colors have to be the same, right?
Yeah. So you're right. So if I go back and talk about colors, then the colors have to be same as well. Yeah. Mm-hmm. So how is it really useful? So what the way symmetry reduction is put into practice is that there's some static analysis that's done in the system, and then you come up with a function that maps each state to its representative, right? And as you do your state space exploration, you don't really explore states. Every time a new state comes up, right, you map it to its representative, and you just explore only the representatives. This is not very easy because in general, right, computing the function which maps states to representatives is a pretty hard thing to do, right? But you could do some things. I mean, for one, you could be satisfied with multiple representatives. So then you would explore more states.
Probably not something that's worth by 10.
Yeah.
But since we can't enumerate the state spaces as large, then there must be symbolic ways of doing this. Symmetry addresses without having the state space.
Yes, people have tried that, and those things have not really worked very well. Yeah. So the thing that, so this is my opinion. See, my opinion is that what sort of works is only this. So you basically ask the user to tell you where the symmetries are, and you can sort of verify statically whether those are actually symmetries using sufficient conditions for symmetry, and that's the approach that Murphy has taken. Right? You have a special keyword called a scalar set, which sort of tells the system where the symmetries are, and then you exploit the symmetries well. And the people who have gone this route, sort of approximating it and computing it, haven't really succeeded yet. Mm-hmm. So that's actually all I'm going to say about symmetry.
What if you just come up with equivalent classes that are not stable? So you lose some, you become approximate, but you still get something much.
Yeah. So then you get abstractions. That's what you get. I mean, you don't get sound and complete abstractions. You get complete and unsound abstractions. And people do that as well. That's a very common thing as well. And so that actually sort of goes into my next top set of things I want to talk about. Daniel.
So does Murphy, is there any special meaning behind the name Murphy, other than the fact that it's Murphy?
I have no idea. Okay. So it's a model checker that David Dill and his students wrote at Stanford, and I don't know what prompted him to choose it. Okay, so the one thing I should say is that there's another tool from CMU called Nitpick, which is used to analyze software specifications. And a lot of this shows up in that as well. So hopefully we'll have a chance to talk about it next time. Yeah.
Do you have an example of symmetric reductions?
Work very well.
Right.
For instance, if you read the Murphy papers, the ones that they found really useful for instance are in coherence protocols, cache coherence protocols, where you have you have 2 or 3 processes, and there's a protocol that's running, and there's an obvious symmetry because for the protocol the processes are all symmetric, right? That's one that was very useful. And again, as I said, right, when you model processes, the general purpose register file is symmetric. Whenever there's a ring or a mesh or a star, there's symmetries that rise out of those naturally. Yeah. So sometimes you can't have abstractions that are this strong, which are sound and complete, but it's okay. And what people do in abstractions is that they sacrifice the fact that they don't want to lose, they're willing to lose information, and they still construct abstractions. Then all that they want to do is that they want to construct some abstraction A such that M is a refinement of A, such that every trace that you can produce in M can be produced by A as well. But A can have a lot more traces than what M can have. And that is still useful because if you can prove that A satisfies some property phi, then that carries over to M as well. But if A does not satisfy phi, you are sort of host, because then you can't say anything. You can't say whether the problem is with the abstraction or whether the problem is with the M. So that because of the fact that you lose information, you can't do much. But the key in these things is to come up with good abstractions. And good is very subjective in the sense that a good abstraction is something that lets you prove a property phi. And the key is to actually construct A from M's succinct description, like either from a circuit diagram or from a process object model, and not from the state space. So I'm going to talk about one popular way that people in the model checking community use to construct abstractions. And there's several papers that have been written which on variations of this basic technique. So the assumption is that, say that my M has a concrete set of variables, V1 through Vm, and say M is pretty large. And for some reason, I have an intuition that I have n predicates, where n is a much smaller number than M, which sort of embody what my system does, as far as the property that I have in my mind is. Right? Then what you do is, you want to construct an abstract system that has n Boolean variables, one for each of these predicates. And the abstract system has just n Boolean variables. And the way you construct this abstract system, so I'm going to describe the way in which you're going to construct the abstract system. And for that, I'm going to describe 2 things, which will sort of become very familiar to abstract interpretation. So you have a concretization function which takes an abstract set of states and maps to a concrete set of states. So for instance, if you have 3 predicates, P1, P2, P3, right, and you have this abstract set of states, 1, 0, 1, 1, 0, 0, then the concretization really is the set of states that is described by P1 and not P2, right? So this is P1 and not P2 and P3, or the other one, right? So the concretization function is very clear. The abstraction function is something that takes a concrete set of states, say S, and it gives me some abstract set of states T, and there's a wide choice here, right? All I need out of T is the fact that when I concretize T, I get something that is bigger than S, right? If I want to be very precise, right, I can define the smallest T, and that is sort of implicitly defined by what gamma is. But when people construct abstractions, they don't necessarily find the smallest T. They find some T that satisfies that, right? So I'm going to go through a technique that it was in a paper by Hassan Saidi and Suzanne Graf, I think a couple of years ago. What they do is how does one construct this abstract state space? So what they do is, suppose I have S, which is an abstract state. The question is, what is the image of S? Which means, what are the states in the abstract state space that S connects to? Right? That's the question I want to answer. If I answer that question, then I've told you really how to construct the abstract state space. The way they do it is actually they first concretize S, which means that they use gamma and go to gamma of S, which is in the concrete state space. And then they compute the image in the concrete state space. This you could do because you have, even though you have a succinct representation of M, you could compute images with, for instance, if you have binary decision diagrams. I showed you last time how to do that. Right? Then what you could do is, what they do is, they take this set and they ask the question, for each predicate Pi, does this set satisfy Pi, or does this set not satisfy Pi? I mean, you could answer yes to one of those questions, or actually you could answer no to both of these questions either, right? Because some of these states could satisfy Pi and some of these states could not satisfy Pi. And what they do is they just use the information that you get from these tests to do this. And in fact, they use a theorem prover to ask these questions, to answer these questions. Oh, I defined it last time. Image is an operator that takes 2 arguments. The first argument is a set of states. The second argument is a system. So if you give us, so M is a set of all arcs, right? So this says if I give you, so for instance, if this is my entire system, right? And if I give you this set, then the image of S is this set, right? So in fact, the succinct representation of M is actually just a description of the image function. That is all M is.
It's the union of the successors.
It's the union of the successors of actually that's the easiest way to describe it. I think. The union of the successors of all the states. Yeah. Mm-hmm. So what these guys do is that they just check for each Pi whether it's satisfied. And just to give an example, suppose I have my state is 1, 0, 0, and say I still have 3 predicates. What they do is they concretize it and they compute the image. And suppose I satisfies not P1 and P2. And for P3, you don't really know whether it doesn't satisfy either P3 or not P3. Then what they do is that they start from 1, 0, 0. They fix 0 and 1 in the image. And then they let P3 just vary. Right? So this is an abstraction. And in fact, you could prove that by construction, this is an abstraction. Mm-hmm.
So you get a possible explosion because of many states that you cannot prove true or false.
You could get a possible explosion. Yeah, you could get a possible explosion. So, but the understanding is that n is much smaller than m. So the number of predicates you have is something much small, so that you have only 2 to the n states anyway. Right? But if you don't prove you are not able to prove a lot of them, what you would lose is you lose precision. You will have a lot more arcs actually. So more arcs in the abstraction is bad. Yeah.
So you're introducing non-determinism.
You're introducing non-determinism. That's what you do. Yeah. So usually the time consuming part in this is not actually the construction, but actually coming up with the predicates. Right? Whatever for property that you want to prove, you somehow have to, because of your intuition from the system, have to just come up with these predicates, and that you can never do automatically. So that's why this abstraction sort of come under what the tools help you do that support abstractions is that you have to do some creative component. You have to either supply the predicates or do something which has a similar flavor, and then the tools will help you build an abstraction from that choice that you make. And almost every abstraction technique that people use in model checking have that flavor. There is a creative component that the tools cannot do by themselves. So it's for that reason that I group abstractions and in fact the next technique under a different head. So where are we right now? So we went through these, and I just gave one way by which abstractions are constructed. But the key behind both these are the fact that you require genuine insight into the design to be able to use these things effectively. Yeah. So now I'm going to talk about divide and conquer, which is implemented in the model checker Mocha that I worked on at Berkeley. Yeah. So the one other thing that I have to say is that so far, when I was describing all these techniques, I was assuming that I'm verifying invariance. And just for this, I'm going to change that. I'm going to assume that I'm going to do refinements. The reason is actually, it's going to probably take a lot of time for me to rephrase this theory in terms of invariance. And also, because I did my thesis on refinements, and divide and conquer was a significant portion of my thesis, so it's easier for me to explain it with refinements. And also, I'm going to convince you that refinements are not so different from invariance, right? So, in fact, the practical way to do refinement checking is to transform the refinement checking problem to an invariant checking problem. So I'll mention that as well. So for the rest of this talk, I'm going to talk about refinements. So let me just recap what refinements are. So refinements show up when you don't specify specifications using logic, but you just specify specifications also using another state machine. So the example was, say you have an arbiter, which is and the specification of the arbiter just says that it says 3 states, F, G1, and G2. Now the colors make sense again. So you can turn your color back on. Yeah. So it starts at F, and then if there's a request R1, so two people want some shared resource. If the first person wants it, he puts a request here, and then he waits for a grant to show up here. And the second person wants a request, he puts the request here, and then he waits for it to show up here. And what the arbiter does is that if both of them request, he doesn't really say which way to go. It just says maybe it goes here or here. This is an implementation of the arbiter in which there's 2 free states. And when I'm at F1 and R1 request, I grant it. But when I'm F1 and R2 requests, I just delay the grant. And when I'm at F2 and R2 requests, then I'm going to grant it. So this is some implementation of the arbiter. So what you have is that when you say that M refines S if the language of M is a subset of the language of S. What do we really mean by language of M? What I really mean is there's some set of variables that I agree beforehand are common to these two. For instance, in this case, the common variables are R1, R2, G1, and G2. Right? So I just considered all possible executions of M. So maybe one possible execution is in the initial state, the state is at F1 maybe, and there's no grants. And then maybe R1 requests. Then I go to maybe G1, and that grants G1. So the implicit understanding I have is that whenever I go here, then this becomes on. And whenever I go here, this becomes on. So this could be one evolution of the system. So what I mean by refinement is that for every such evolution, right, if I just forget about this and take the values of R1, R2, and G1 and G2, then I could produce some other execution of this system that has this behavior as well. Mm-hmm. The homomorphism is usually stronger. Okay. If you talk about homomorphisms, then you talk about simulations or things like that, which imply that. Yeah. So in fact, the way people check refinement actually is they check for homomorphisms. And checking for homomorphisms is sort of like invariant checking, as I would convince you in the next couple of slides. So the way, if you want to really check refinement, you have to actually do some automata theory. You have to take this as a language containment problem. You have to complement S and do these things, and that's complicated. So in practice, what the assumption people make is suppose every variable in the specification is also present in M. right? So it means that your specification doesn't really have any new variables. In that case, then refinement checking reduces to checking this, right? For every transition, reachable transition of M, right? Suppose I could go from U to V. Then I have to check that if I restrict U to the variables that are in the specification, right? This is the valid thing to do because every variable in the spec is also present in the implementation. So I could take U, I could restrict it to the variables present in S, and I could get a sensible specification state, right? So what I could do is, instead of checking whether, I have to check for every reachable state U, every reachable transition that M can take, S can also take. Mm-hmm.
So you may have some condition, some sort of notion of an extended finite state machine of an enabling condition for a transition.
Yes.
Right. So if one of those conditions refers to one of these variables that is in I see. So basically, if you have this expression and it's referring to one of these extra variables that's in M but not in S.
You could have variables that are in M but not in S.
You'll just throw that out of the
That's
equation.
Right. That's right.
And you're going to get a suit. You're going to get a.
So for every actual transition that I can make, right? So if I just draw out the transition graph of M, for every reachable transition I make, I require that if I project out, so for every transition that I can make, right? So suppose this is my state transition graph of M, right? I have to check that for every reachable transition that I can actually reach from the initial state, that if I just project out U, I get a specification state, US. And if I project out V, I get a specification state, VS. That this arc actually exists in my specification. That's what I have to check. And this is like an invariant checking problem, right? Because I could phrase this as a transition invariant. Right? Now the invariant is on the arcs and it's not on the states. But it's the same thing. I mean, you just have to check, you have to just explore the state space of M. And as you're doing every step, you need to make sure that the step satisfies certain property. So again, invariant checking is very useful. If you could check invariance on hardware pretty well, then it's already pretty good. And the complexity is sometimes, yes. But you could have some variables in S that are not present in M. In which case, you could get some guidance from the user and write these functions, which are, I call them as witnesses, but I've heard the term abstraction functions or homomorphisms. They are all sort of the same thing. Is that you sort of write a function that maps the implementation state to what those variables are. And I could give an example for that. Right? Suppose I were to do refinement checking using invariant checking for this particular example. Right? So the hidden state here is this state, right? The specification state. That's sort of new. That's not present in my implementation. But I could sort of have a mapping which says that whenever my implementation is in F1 or F2, then my specification should be in F. Or whenever my implementation is in G1, then the specification should be in G1 as well. So now we could put these together, and now my condition is satisfied, that every specification variable is also present in my implementation. And now I could check this as an invariant. Okay. So this is actually not, I'm not talked about divide and conquer it at all. So the reason why I had this lengthy discussion is because refinement checking is really invariant checking. And
coming up with that mapping,
it's usually not hard.
right?
Yeah, it's usually not hard. What's hard is that you require to do scalable refinement checking. You need another mapping which goes the other way, and that usually is extremely hard to do. Huh?
You don't want to enumerate the M. Right. That's one.
Well, yeah, you don't want to enumerate. So the hard. I mean, Jakob's question was, is it hard to come up with this W? And my answer was that, in my experience, whenever I had to come up with W's, it has been easy. But I'm going to talk about other things that you have to come up with in the next couple of slides. It's usually, but the thing is that the creative process has already happened when you're writing the spec.
Right.
Yeah. So usually what happens is that the creative process has already happened when you're writing the spec. It is just actually continuing the creative process and just writing it down completely. Right. So the other difficulty where divide and conquer really is useful is that, I mean, even then, right, even though I say this, I still have this huge state space that I have to deal with. And divide and conquer can be used to do that. And the way you do that is as follows. Suppose I want to check whether, the idea is that I have state machines and I have composition between those. when I want to actually reason only about individual state machines. I don't want to put them together. So in effect, what I want to do is maybe I have state machines P and Q, and I have specs P prime and Q prime. What I really want to do is I want to just reason about individual components. I want to say that P defines P prime, Q defines Q prime, and I want to put them together. But usually, this is actually a sound rule, actually. But what actually happens is that this is true, and these two are not true. And that's not surprising, because the people who constructed P made sure that P worked only when you put it in where it should be put in. So if you just excite P using arbitrary things, then P can do strange things, right? But then if you want to analyze it, then you have a huge state space. So what assume guarantee rules try to do is that they try to set P in a very abstract environment, right? So instead of just setting P and letting it go freely, you try to verify P in the context of Q specification and not Q itself. And one thing you have to be careful when you do this is the circularity, is that you are assuming Q prime to prove P prime, and you are assuming Q prime to prove P prime, and the rule could be unsound unless you are very careful.
What are the red boxes and the yellow boxes representing?
So the red boxes are all implementations.
And
The M. The red box is the M. The yellow box is the spec S. Yeah. Right? So, and this is the proof rule. If this and this is true, I want to actually conclude this. And there's a line here. It just means that P and Q are some blocks, and maybe they're hardware, and there's wires that used to talk to each other. Oh yeah, there could be a bunch. Yeah. So you could just think about them as chips, and they're just communicating with each other.
Okay, so you're saying that P composed with the specification of Q on the left side of the refinement.
So I want to actually have a rule which, if I prove these things, I want to show that this is true.
Right. Okay.
But I am just cautioning the fact that this might not be a sound rule all the time. Right? And I'm going to give an example as to one place where this could not be sound. So suppose I take this example. Right? I introduced this notation last time. This is just describing systems using guarded commands. And I have two variables here, A and B. So this says that if this condition is true, I could do this. That's all this is saying. And I use the notation primes to denote the new values of variables in a particular round, right? So the specification says that B is always true, and the specification of Q says that A is always true. The implementation assume that all variables are initialized to true. So when you start off, A and B are both true. And what this system is doing is it first checks what the previous value of A is. If the previous value of A is true, then it retains B to be true. Otherwise, it makes B to be false. And same as that. So intuitively, right, this should refine this, right? Because you start off with true, true, and then in the next step, there's only one way: true, 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 and so on, right? But suppose I change the system slightly, and then in each step, instead of looking at the previous value of A, I look at the current value of A, right? And instead of looking at the previous value of B, I look at the current value of B. Then, I had this flying X that come.
I always thought that this notation on the left side always was talking about unprime variables.
So you could talk about prime variables as well. I mean, if you talk about prime variables, you have to be careful about what the semantics is.
Yeah.
So the semantics is.
Because the prime is the value in the next state.
So for instance, when you talk about circuits.
And usually guarded commands are talking about the transition, state transition. You're defining the state transition. So what does it mean to have?
Oh, okay, I see what you're saying. So what happens is, suppose I have, so there's two kinds of machines called Moore machines and Mealy machines, right? If you have those, what do you describe as sort of Moore machines?
Okay.
These Mealy machines are those in which, in a single round, a lot of interaction can happen during the round itself. But there shouldn't be any causal loops, actually. In this example, there is actually a causal loop, right? So I could give a semantics for this. The semantics for this is, I start off with true, true. So this B is true and A is true. And there's two possible next states. One is B is true. Actually, yeah, this is a possible next state. And then I could also go to B is false, A is false. And the semantics is, if I take this to be my B prime and this to be my A prime, I could say which guards executed it. So I could give semantics for these using this way. This thing is unstable. Yeah. Yeah.
Then you can couple more R's.
Yeah. So I could have this as well. Yeah. Yeah. So this is the state transition system for this system. Right. So this is unstable. Right. But the point I'm making is that you have to be careful about your model when you talk about assume guarantee rule. If you have a model that is like this, then the assume guarantee rule does not necessarily work for this model, because we know that this refinement is not true, right? But if I take P and verify it in an environment of Q prime, which always keeps A prime to be true, this refinement holds, right? And also the other one as well. If I take Q and put it in a context where B prime is always true, this holds. And from these two, I cannot conclude that if I put P and Q together, I cannot put P prime and Q prime together. So what you really need is that you need to have some sense of induction over time, actually, to make these things work. So what you end up doing is that at least one of the assumptions you have to make only up till time t minus 1, tau minus 1. And the other assumption you could still make until time tau. And the one way in things like circuits, right, it doesn't really matter, because in synchronous circuits, you cannot have combinational loops. So if all these things are synchronous circuits, then you need not worry about circularity at all. The fact that there's no combinational loops in your system would mean that you could just do this and everything would just work automatically. So that's about assume guarantee. So if I try to draw this as a circuit, right? If I try to draw this as a circuit, so I could have some latch that describes A here, and then some latch that describes B here. And there's two wires that come in. I mean, the previous value is A, and the new value is A prime, right? I could just describe these systems as combinational circuits that connect these things, right? So if you try to draw a circuit that connects these, then you would find that they would look somewhat like this. A prime is connected to B prime, and B prime is connected back to A prime, with no latch in between. Mm-hmm.
That's a little feedback. It's not a latch that breaks all feedback. And the latch is designed such that it's fast enough to use the edge triggered effect.
That's right. That's right.
That the combinational logic output can't go back to the input for the combinational logic.
That's right. That's right.
You have to latch instantaneous motion. Go to the next stage.
That's right. Because if you have circuits, right, that are synchronized and are not unstable, then this problem doesn't really arise. There's a natural induction over time that helps you do assume guarantee proofs over those things. Yeah.
But this is the theoretical knowledge. Many of those look at whether the program from hardware,
Will have no causal loops, you're saying?
won't have any.
No, but the thing is, what happens is that the systems won't have causal loops. But sometimes you might want to write specifications which are not even executable, right? So for instance, in Mocha, for instance, we would write. So this is a circuit, and for the circuit, I want to write a spec, right? I just write the spec saying, suppose x and y, x, y, z are three variables in my circuit. I would just say if x equals y, then z equals 1 or something like that. Sometimes it is convenient to specify circuits, convenient to write specifications of circuits which are not necessarily executable. And if you start doing that, then you have to be very careful about circularity. Yeah.
Right. But it's not a feature of the real system. It's a problem with the refinement.
Yes. Yeah. So you have to be careful not about your system model, but also about the way your refinement methodology is set up when you try to do these things. So, but you could always make reasonable choices so that this problem doesn't arise. The other problem that comes up is that if you try to verify real systems don't look nicely like P, Q, P prime, Q prime, right? So what ends up happening is that your system is a mess which has some inputs and coming in and some outputs going out. And then your specification only talks about the relationships between X and Y. And then you can't usually do divide and conquer because there's no P, Q, P prime and Q prime sitting there waiting for you to decompose, right? So there, what you need to do is that to do assume guarantee reasoning in those circumstances, you sort of have to manufacture what A and B are in your spec as well. You have to sort of expose what the hidden interfaces in your system are, in which you're going to cut and do proofs. And I call these as refinement maps, and those the user has to write as well. And that's actually a very hard thing to do.
You're looking for the program.
Those are very similar to that. Those are very similar to that. And those are very hard to write. Unlike the witnesses, which are actually very easy to write. Because you sort of know what the witnesses are for, because when you write the specs, you have the witnesses in your mind. But even when you write the specs, you don't have these in your mind. So those are very hard to write. But if you write them, then you could use them to split your proof. Like for instance, so this is an abstract specification of what B is, and this is an abstract specification of what A is. And if you write them, then what you could do is, you could verify Q separately, feeding the abstract A instead of the concrete A. And then you could also verify P separately with the abstract B instead of the concrete B. Right? So, Mocha... Okay. So, Mocha implements these things. And I'll give a flavor of what it takes to do a refinement checking problem in Mocha. So you have these modules, which are the implementation, and you have modules that implement yours, that are your specification. So the user has to do two kinds of things. They have to write these white things, which are actually witnesses. So these actually say what the hidden variables in your spec are. And then you have to also write these refinement maps, which sort of tell you, give more room for the proof to be split. Right? You might choose not to do these as well, or you can choose to write as many of these or as less of these as you want. But the thing is that you write a bunch of them. Whichever interfaces you can specify, you just write them, and then.
So the funny sort of thing, though, there's something counterintuitive in that you're expressing detail from the implementation in the spec in order to get modularity in here.
Continue to divide and conquer.
That's right. Isn't that the only way to divide and conquer? Yeah.
But you're exposing the internal state.
You're exposing it in places where you can state something sensible. Otherwise, you can't do the proofs. Yeah. I mean, you're exposed. I mean, so I use actually a BDD-based model checker to drive this thing from the bottom. But whichever parts I can verify without exposing the interface, I just verify. Right. And when my BDD-based model checker just dies, then I just help it by exposing the interface. So I have about 3 or 4 minutes. Let me just finish this pretty quickly. So the way you do refinement checking in Mocha is that you write these things, and then Mocha just takes over. It just does it does everything else automatically, at least the laborious parts automatically. It takes each specification module, it finds what the corresponding implementation module is. Then it uses some heuristics to find an environment for it, and then tries to do a proof. So it does those things by itself. But still, the creative component is actually to write those witnesses and those refinement maps, and that the user has to do. And there's a bunch of things that we successfully verified. We verified protocols, several pieces of hardware, including a really large piece that this thing says a VGA processor. This is something that we did not write. All the other things we wrote. So if I have 3 minutes, I can just tell you what some experiences about the verification of the VGI. This was designed by another group at Berkeley for web-based image processing. Just to give you an idea of how big this was. This is a single processing chip, and it has 6 processors. And each processor has about 30,000 logic gates. And each processor is it has a 3-stage pipeline, and the processors are all talking to each other using complex handshake, which has been optimized for performance. But the way the interconnection between the processors is configured statically, which means that you know ahead of time which processor is connected to which processor. So one of the important things of this project was to actually come up with a spec, because when we were given a large portion of VHDL code, and that's it, that's the system. And so for a while we spent a lot of time. We want to do a refinement check, so this is the only thing that we got. So we spent a lot of time trying to figure out what this must be. So the way the system works is that you have a bunch of processes. All these circles are processes, and each of them is executing its own code. It has its own instruction memory, and it's running some instructions. And each instruction, what it's doing is that it is maybe sucking some data from the inputs, doing some computation, and maybe updating its own internal state, or maybe just plugging some more data out on its out arcs. This thing is supposed to be doing things like MPEG decoding and things like that. So what it is supposed to do is that like the MPEG data, the image stream, is coming from the left to the right, and all these processes are just simultaneously acting on it and transforming it in some various ways. And so what you're doing is computing some like fast Fourier transform or something like that. That's what you do with these things. So so the one thing that was so how, when we write the specs, right? So we ask the question, how does a programmer to the VGI look at the VGI? I mean, does he understand all these details of this pipeline and all these details of this complicated handshake when he has to write programs in it? And the answer was no. The programmer has to assume he cannot make any assumptions about the time delay in the pipeline. For the programmer, the pipeline should just look like an ISA. And for the programmer, the handshakes must just look like FIFO buffers. You cannot make any assumptions about what time it takes for the data to go from here to here. So for that, because of that, you could write a spec which sort of looks like this. And when people write programs, this is what they have in mind when they write programs. And it's very nice because they were very happy when they wrote the spec. Because now what they could do is they could write a simulator which is based on this spec, which is much more efficient than this. Right? So when you have a program, you could find its behavior just by running it on this, which is much quicker than doing this. And what we had to do was we need to check that this actually refines that. And now this is actually, I could phrase it as a refinement problem. And this is huge because this has, each one of these has 800 memory variables. And like a BDD based model checker just runs out of steam at 50 or 60. So we had to spend a lot of effort writing both witnesses and refinement maps and split this up into smaller proofs for a BDD based model checker to work. And we found 3 bugs actually that made it to the first tape out. So they had fabricated the chip, and after that we found that there's 3 bugs. And the second tape out, they fixed all the 3 bugs actually. And for the portions of the chip that we modeled, we actually proved that there's no more bugs that remain. And I could just give you a flavor of what kinds of bugs that we found. If I can take 1 more minute of your time. Okay. So the kinds of bugs are, say this processor is doing a computation, which has to write data to both these things. And say at that particular time, there's space in this route, but there's no space here. Maybe this route is completely full. So this processor has to remember, it has to send the data token here, and it has to remember the fact that, hey, I have sent the data token here, but in my internal state, I have one other token that this guy it's still pending for this route. So that happens, and after that, after a while, 2 things happen simultaneously. This processor becomes free at some instant. There's room here to get that data. So it says, I'm now ready. And at the exact same time, the next instruction is executing, and it wants to write data as well. So there was some particular timing problems under which the old data will get clobbered, and that they could never find using simulations. Right? So the model checking could find the exact sequence under which that would produce the error, and it was actually fabulous because we would fix a bug, and the model checker would tell us what about this, and it would give us another error trace, right? Which actually showed us. So when it gave us an error trace, it gave us an exact sequence of instructions and the timing, which actually violated the refinement map. So it was a lot of fun to do that. Yeah. So that's it. So next week, I'm going to switch gears and talk about software. I'm going to talk about very soft. I'm going to talk about a thesis from MIT that Dan Weiss suggested that I read, and some work in specifications. Yeah. Thank you.